So chemical separations are immensely important because whatever detection system we devise to be responsive to an analyte, it's important often that that analyte be by itself when it's being measured to avoid interference in whatever that analytical signal is. And so often, most often in chemical analysis, we actually have a coupling of two processes. We have a separation step where we pull out analyte or analytes from a complex matrix or mixture, and then we measure their signal from whatever our detection scheme is. The two large, or sort of big categories of separations that we'll discuss in this series of videos are extractions and chromatography. And both of them rely on the phase transfer of a solute that's dissolved in something. But with extractions, we're talking about transfer of solute between typically two or more mobile phases. And so the picture I have here is the type of liquid-liquid extraction that many of you would have done if you've taken an organic chemistry lab course where you produce a product in one phase and then you extract that product to another phase using different properties of the chemicals. Often pH is one, or polarity. Chromatography is slightly different in that it's phase transfer, but typically it's transfer between a solid, what we call stationary phase, and a liquid mobile phase. And so instead of two mobile phases, we have something that's not moving, which interacts chemically or physically with our analytes and our matrix, and then something that's carrying that through that stationary system. And so if you've taken, again, a organic chemistry lab course, then many of you have run what's called column chromatography or thin layer chromatography. In both of those circumstances, you have a fixed chemical substrate, typically silica gel, and you leverage the polar interactions between your chemical species in that silica gel while you pass certain solvents as the mobile phase. So those are categorically just two general different systems and situations, and we're going to start this video with extract. So like any chemical system, when you are moving one species, in this case we'll just call it S, some solute, between two phases, the exact concentration that will remain at equilibrium between those two phases is going to be set by some equilibrium constant, which of course is, the underlying governance of is thermodynamic in origin. But if you shake this thing up and you just allow it to sit at equilibrium, at some point the ratio of those two concentrations that partition between phases is going to be set by some constant. That's as simple as it gets for extractions. And the extraction efficiency can be thought of using this expression where Q here, again Q being overused in chemistry, but Q here indicates the fraction of the particular solute that remains in the original phase, and we'll call that phase 1 in this case. That's going to be equal to V1, which is the volume of phase 1, divided by V1 plus the equilibrium constant for that separation, or the partition coefficient here, multiplied by the volume of the second phase, and then all of that raised to the n power, which denotes how many times you're conducting that extraction with these volumes and these variables. So let's see what that might look like as an example. All right, so let's pretend that we have a system of toluene, which is a nonpolar solvent, and water, both phase separate simply based on the differences in their polarities and densities here. So you got toluene on the top, which you've got about 500 mils of it, and then phase 1, the original phase where the species is present, is at 100 mils, and we've got originally about 0.010 molar concentration, and the equilibrium constant for this separation lies towards phase 2 in that it's 3. So let's just assume for the first example here, let's assume n equals 1, meaning we do this one time. So we mix these things together, we shake it up really good, we allow it to reach equilibrium. What is the equilibrium concentration, or in other words, computing Q? What's the fraction that remains in the first original phase, the aqueous. So that's just a plug and chug. So we toss these values into our expression for Q, and what we get is a fraction of 0.062, which if we multiply it by 100 to just get a percentage, that indicates that only 6.2% of the original 0.01 molar remains in solution after that initial extraction. So we could multiply that 0.062 by the 0.01. That would tell us the concentration in phase 1, and then 1 minus that would give us what our, or 0.01 minus that would give us our concentration that is in toluene. Okay, so now let's assume you do this extraction 5 times, which means after the very first extraction, which we did here, you would take that 500 mils toluene layer, or I'm sorry, you would drain off that toluene layer, put a fresh one on, and then extract what remains in the water, and you do that 4 more times. And so same expression, except now we're raising this whole expression to the power of 5, which gives you a value of less than 0.1% as we extract this 5 times, which is the nature of why, if you're trying to analytically extract all of the products in a particular reaction, or from a particular solution, if you want to extract as much of it as you can, doing multiple separations of small volume is going to be far more efficient if you look at this expression than it would be to do one large volume extraction. In other words, if we did this one time, as in we did this in one large extraction, where instead of using 500 mils 5 different times for 5 subsequent extractions, which is what we did here. Instead, if we just use the same volume total, which would have been 2,500 mils, 5 times the original 500 for the toluene layer, we just did that all in one big extraction, what we get is about 1.3 remaining in the solution as opposed to 0.1. So it's about an order of magnitude more efficient to do small volume multiple extractions than one very large extraction. This is always going to be true. Okay, good example of this, as I mentioned before, is in synthetic chemistry. So if you've taken an orgo class, then you've probably used one of these. These are a separation funnel or separatory funnel. These are designed for a liquid-liquid extraction. Typically, you produce a product in one phase, maybe there's some byproducts there, and you separate that product out to another phase by protonating it or deprotonating it, or leveraging differences in solubility between those two phases for whatever reason. And so I'll just show you a quick video of what that would look like if you haven't, or if you have, just to remind you now in this context, so the next time you do it, oh yeah, maybe I should do that 5 times, but really small volumes, rather than doing it all in one big pass. So here they're setting up the SEP funnel. So they're just closing the stopcock. Now they're adding the 2 layers here. So this is the aqueous layer. There's some dye, there's some green dye in the aqueous layer, and then that top layer that's less dense is the organic layer. You cap the thing, and then of course you're going to have much higher surface area of contact if you shake this thing up, which will increase the extraction efficiency. That can create gas as it's displaced, so you vent it while it's upside down like that. Keep shaking it, keep shaking it. The goal here is just to reach equilibrium faster. Shake, shake, shake. Vent, vent, vent. And now you can see in that bottom layer, there's sort of a distribution. Instead of it being purely green on the bottom, there's sort of 2 different layers. And now for the collection of the 2 layers. So first, the more dense aqueous layer, that's going to get pulled off. So make sure to pull that off. So you pull this off. And so now you're left, that's the aqueous layer, now you're left with the organic layer on the top. You can pull that off. And if you're going to run this multiple times, you'll collect the organic because that's where you've extracted your product into. That's what you want. And then you'll replace your aqueous layer back into the subfunnel, add fresh organic solvent, and continue to conduct this as many times as necessary to extract what you deem as reasonable extraction efficiency in your setup. Note that we're sort of talking about two different things here. I'm talking about extraction in terms of pulling an analyte out of a matrix so that we can analyze it later. It's a little bit different reason, as is the case in organic synthesis reaction, where you're trying to extract a product to be used in subsequent reactions or to weigh it out and compute a yield or something like that. So typically the end goal of these two processes are different, but the mechanism to get there is the same, using a simple liquid-liquid extraction system like this. As you can imagine, there's several different ways for you as a chemist to perturb this equilibrium value, depending on the nature of these two phases. And there's lots of different ways to do this, and people over the last 100 years have made their living off of doing this and figuring out creative ways to do this. And this typically comes down to leveraging what you know about wet chemical methods and equilibria. And so there are methods where you can utilize pH to increase the solubility of a solute in one phase over another, which could change or augment the equilibrium K value for that partition. Or you could imagine, say you have something in the toluene layer and you want to pull it into the water layer, and maybe it's something that can complex well, and you understand that chemistry. Then what you can do is load up your aqueous layer with a complexing agent, something like EDTA, and that we know the binding coefficient Kf, formation constant, for EDTA complexes is so large that's going to compound into the overall separation equilibrium constant. And so it's important to think that we've learned quite a bit about aqueous equilibria, and those things play a significant role. Now you're thinking about them in terms of, well, how do I leverage equilibrium that are really favorable between two phases to extract more, or quantitatively or analytically more, of a particular solute into another phase for subsequent analysis.